Hi, in this short video, we will introduce a algorithm which converts a CA solution to a discrete solution for facility location problems. And this algorithm is called a disk model algorithm. First of all, what is the goal of this algorithm or this video? What is our input? What do we have on hand? We're now considering a facility location problem on a continuous region. Every single point could be our candidate facility location. And we want to establish a finite set of facility locations such that our objective, the cost function, is minimized. And right now, we have introduced the continuum approximation algorithm, which gives us a service area function. It is not the final solution of the facility location problem, but it's a continuous function defined over the entire region. And the meaning of this function is that according to the CA estimation, around each point x, we will like the service area of a facility if built around x being A of x. That is, for a different point x, we have a different target service area. And finally, we want to establish many locations on the region such that each of them is allocated to a service area which is close to the area of x, the A of x given by our CA solution. And right now, we assume this A of x is given. And our goal, what do we want? Our goal is to find the actual number of facilities we want to build and their concrete locations. We want the set of n locations denoted as x1 all the way to xn in our region. And which set of solution is the better we want, or which one is the one actually induced from our CA solution? Actually, we want our service area of the facility approximately equals to the service area given by A of x. Consider I have a solution like this. Each dot represents a facility I want to build, and each circle is the service area given by the CA function A of x. And given all these dots in the region, I naturally have a service area according to the Voronoi tessellation. Given these locations, consider this facility xi built in this position. Its service area is given by the hexagon-shaped area denoted here. So our goal is to have, for each facility, its actual service area, as close to A of x. And you might be interested in how this hexagon-shaped area, or maybe it's not necessarily a hexagon, it could be a polygon. How is this shape derived? It's called the Voronoi tessellation or Voronoi diagram. It's pretty straightforward. The meaning is, for every point on the region, we find its closest facility, the blue dot. And for example, here where I'm pointing at, this point is closest to this blue dot. So this point belongs to the service area for this blue dot. So you can imagine how this Voronoi diagram is constructed. For example, let's look at this line. This line is the vertical bisector of these 2 points. Of course, in terms of algorithm, there are certain ways to finally construct this shape, but you should know this boundary between the 2 service areas is defined by the vertical bisector of this line connecting the 2 centers. Alright, let's see how the disk model give us the set of solution from the service area function A of x. In the first step, we want to estimate the number of locations from the area function. And the way of doing it is n equals to the integration of 1 over a. and it's integrated over the entire domain. And of course, n has to be an integer, and we take its rounding integer. And you might want to ask, why are we integrating 1 over a, or 1 over a of x? Recall that the meaning of a of x is our desired service area for each facility close to the point, the coordinate x. So what is 1 over a? 1 over a is a density. It's the desired facility density around x, or it's the number of facility per unit area induced from the a function. So the total number of facility is the integration of 1 over a. Consider you integrate a density of a object, you get the mass, right? You integrate the density of facilities, you get the total number of facilities in the region. And then next, we randomly generate n locations on our domain. And in our example, we pick domain 0 to 1 from x and 0 to 1 range for y. Just randomly generate n locations, and we can draw the circles for each location. For each circle, its center is our location xi, just randomly generated. Its area is given by the function a of x. And its radius is naturally defined by this area, which is a radius such that pi times r squared equals to a. So the radius is square root of a over pi. So you can draw a picture like this. Each center is your facility, and certainly they are not in the desired shape because their service area has many overlaps. And in terms of the Python lines, here is the block that achieves these steps. In this line, I do a integration using a built-in function or from a package that gives me the integral of a 2D function. And in this step, I randomly generated n locations. N is my rounded integer from the previous step. And for each location, it's defined by an xy pair. And I simply use a uniform distribution to generate the coordinates. And next, we want to move these circles or these disks in a direction that is desired. We move the circles by computing their forces. There are two types of forces. The first is called a boundary force. If we have a circle that goes beyond the boundary, then we want this circle to be pushed away from the boundary. For this circle, you can see it has some overlap with the boundary. So the boundary induces a force in this direction. Also, we have forces between each pair of circles. It's called the terminal force. If two circles overlap, they push each other further. For example, consider these two circles. This circle has an overlap with this one, so it will push the lower circle further away from it. So we have defined the forces. And of course, for each circle, for each disk, we compute its total force. And this is achieved through the following lines. I have a way of defining my boundary force. Of course, it's defined in another function. And also, I have a way defining the terminal force. For each circle, I first compute its boundary force, and I add all the other forces caused by all other circles. And I obtain the force on the single disk J1. The next step, I do all the computation for the other circles. And next, we would like to move our disks along the forces. We want to determine the direction and the distance for each move. And this move is simply determined by the force times a step size, a scalar. And how do we know we are good enough? We need to stop. Of course, if all moves are zero or short enough, we claim that we reach a very stable distribution of locations or the disks. So we stop the algorithm and output the location. I have a flag cut if it's in the range of the tolerance. If it's not, I turn the flag to false, and later on I will continue my algorithms. Otherwise, I will jump out from my iteration. The iteration is not showing in this code, but you just need to understand we have a stopping criterion like this. And if the moves, for example, you see these moves are certainly not zero or not small, we want to actually move the circles to a better position. So we move the circle along the forces, and then each circle will get to another destination, and we start the algorithm step 2 once again from the new locations. This is achieved in this line. Location I, if it's in the tolerance, we terminate our algorithm. Otherwise, we move the locations along the forces by a small step size. And you can visualize the algorithm like this. In the first step, I randomly generated, in this example, 11 locations, and of course they're really bad locations. They have many overlaps, and the force is of course large. And then I compute the forces, and in the next step, they will be moved along these directions. In the next step, the circles are moved along the directions to better locations, and this procedure continues. After several steps, you will see the circles are separated from each other at the best they can. And after sufficient computation, it will result in a kind of stable distribution. In this way, we have our facilities locations allocated on the entire region according to our CA solution. Always remember the area of this circle is defined by A of x. Given the point, the coordinates of this point, I compute the area A of x and draw the circle. A of x in this example is defined somehow smaller here in the bottom left and larger on the top right in this square. And if I keep run this algorithm, you will reach a better distribution of the locations. And I didn't make it an animation in this script, but instead I just close each figure and let it run next steps. Of course, I don't have to do that. I can just turn off the plot of the output and let the algorithm run for sufficient time or number of iterations. And here, after 1000 iterations, I end up with a distribution like this. And along with the circles, I also plot the Voronoi diagram, and you can see each circle approximately covers the area of the polygon, and their area is close to the Voronoi diagram shape. Finally, when we introduce the algorithm, we haven't rigorously defined all the hyperparameters, and it's important that we know there are certain hyperparameters affecting the performance of the algorithm. First of all, how do we define forces? How do we define the magnitude? For example, there is one way of doing it. We define the terminal force like this. If two circles is close enough, we define a large force. If they are distant from each other, the force is smaller. If they are distant enough such that their radius, they don't overlap, then I don't apply any force on both of them. Similarly, I can define a boundary force in some pattern. If my radius, my circle does not touch the boundary, then I apply no force. Otherwise, there is a positive force on the right direction, which is perpendicular to the boundary. Also, we need to define the step size. Remember, the step size defines how far we move the circles. The forces determines a relative magnitude and a direction. The step size just defines how far we move those circles in each direction. If we take a large step size initially, and you will quickly get away from the bad solutions. But you will less likely get in the optimal solutions because you are moving too far in each step. So normally people take a diminishing step size for converging algorithms. Also, we have a tolerance parameter. When is the overlap negligible? For example, in a previous solution like this, there are still some overlaps, but we know that they are far away from each other. Do we just terminate the algorithm, or do we take other measures to keep the computations? We need to define a small tolerance. For example, we know that these two circles, even though they have a small overlap, the force is small enough, and we can ignore that and just safely say we have reached a good solution. And next, it's not guaranteed that we always reach a stable solution. So to guarantee a solution, we can reduce the size of the circle. Recall that the radius is given by this, a over pi, square root of a over pi. But if this radius is too large for the entire n circles, n disks, I can just reduce the radius so that they are initially started with a smaller radius. And I changed this pi parameter in the denominator to k, and k could be any integer that is larger than pi. So we are guaranteed a solution when k is large enough. For example, we can play with this circle size parameter in the algorithm like this. Here is my k defined. If it's pi, if it's 3.14, you will have a circle, the disk size that are relatively large. And finally, it's likely that you will have overlaps for each circles. And you can also increase the size for circles. For example, if you pick 10, which is, you can increase the value of k and reduce the length of the radius. For example, if k is 10, and you will have very, very small circles, and likely the algorithm will terminate in very few number of iterations because they're small and they don't tend to overlap with each other. So we want to gradually increase k from pi, for example 4, such that we find a satisfying solution. It could be like this. If k is 4 and k is 5, you will get a solution that is much more making sense. And to sum up, this disk model algorithm converts my CA solution, which is a continuous function defined over my region. The function represents a service area function for each location. We convert that to a set of discrete locations. And this is our final solution for the facility location problems. And this algorithm is pretty necessary if you are solving a pretty large scale facility location problem. For example, here we can try to reduce the service area, which means that we have much more facilities to build. Let's see. And it's likely that you're not going to find a set of discrete solutions or optimal solutions simply through non-convex optimization. That's why we have the continuum approximation algorithm and then the disk model to get us the final solutions.